how can you use boundary conditions to adjust and stabilize your simulation models? In this video, we are going to review a very interesting alternative when using boundary conditions to increase the stability of our simulations. And also, we will see the high importance that the definition of contact interaction has in our results. As we were looking in previous videos, the definition of the boundary conditions are going to be crucial to obtain a correct and realistic behavior of our simulations. Most of the times, we are working with larger assemblies, and the customer could request us to be focused just in one region of the complete model, just a component or a reduced group of components. To go from a complete assembly to one region, we have the option of submodeling, which is very powerful, and I have videos pending to enter into detail of it. And the other option, and my favorite one, is understanding how the component is interacting with the entire model and reproduce the same behavior in a more simple and reduced analysis. In previous video, we were working with this fork of a forklift structure. When we analyzed the complete structure, we had the load condition under a remote mass, and it was compensated by both forks. However, when we wanted to work with only one fork, I had to obtain the equivalent force in the perpendicular direction to avoid instability problems. Well, in this video, I want to show you how we can use exactly the same remote mass by the help of the boundary conditions to guarantee the good performance of the simulation. In addition, we will see how important are the contact interactions in our simulation model and what do we need to do to have more realistic behavior. Okay, subscribe if you haven't yet, let's get into it. Hi, Carlos here, and for those of you who don't know me yet, I've been more than 12 years validating real engineering FEA projects across different industries. So I created my validation method to train FEA the way industry actually demands. You will find all the details in the description below. Now let's continue reviewing concepts of that methodology. Okay, here we have the forklift structure we were working with in previous videos. As we said, we had the definition of the boundary conditions restricting where the structure is connected to the rest of the vehicle in this region, and here in the forks we have a remote mass representing the heaviest object that this vehicle can lift. I reduced it a little bit from the one we used before since I didn't want to overlap the yield of the material, considering that this is a linear static analysis. Okay. The issue that we want to develop here today is the effect of the remote mass when we move to the individual fork component analysis. Here, the remote mass is acting in the two forks simultaneously, and we want to see how we can study this scenario in a simulation of the individual fork itself. So I will move to the fork simulation. Here we are. This is the last simulation we prepared for this fork where we define the wall contact interaction where the fork is touching the structure and the behavior was really good. Now what I have done is to add the same remote mass that we were using in the complete structure. So let's see what is the effect. Before we press the button, we need to think how the simulation will behave. Looking from this perspective, we will have a deformation in vertical direction, but due to the misalignment of the remote mass, we will see a rotation in the fork. Let's see it. I will run this study. Okay, what we can see? Exactly. The remote mass is provoking this twisting of the fork. And this effect is not happening when we work with a complete structure since we have two forks and the load is compensated in both sides. If I animate it, we can see the behavior that we have. So this twisting is not realistic. I will exit. Okay, so then which options do we have? The first one is to use the equivalent local force in the perpendicular direction as we did in previous simulation. The second option would be to have in this analysis the other fork and work with both of them, which is also valid. And the third option, and the one that we are going to use here, is how to use the boundary conditions to calibrate this equivalent analysis using the same remote mass and keeping the same behavior. Let's come back for a moment to the complete structure. Okay, here we are. I want to check the displacements of this simulation. So I go to displacement. Okay, here we have them. After reducing the load, now I have a maximum displacement of 9 mm. The thing is that most of the displacement is happening in the vertical direction. But how much is the portion of that total displacement in the transversal direction, in the Z direction? Let's take a look. I go to displacement, right click and select edit definition. And here I'm going to drop down this menu and check the displacement just in Z direction, which is the transversal. I will accept, and here we have the results. Okay, if we had around 9 mm of total displacement in our fork, in the transversal direction, we just have 0.03 mm, which is practically nothing, right? Therefore, we could use the assumption that to simulate this event, we can consider no displacement in the transversal direction of the fork. Good. Then, considering all the types of boundary conditions that we have reviewed in this channel until now, which is the first boundary condition that comes to your mind to restrict only one translation? Exactly, the roller slider. Let's go back to our fork simulation. What we are going to do now is to restrict the displacement in the transversal direction of this face of the fork. Then I go to fixtures, right click and select roller slider. I will select the internal face of the component and I will click OK to accept this definition. Okay, now let's run this study. It's important, before I click on run, it's important that, well, now we are restricting this transversal direction. But when we do this kind of calibration or adjusting our individual models just to represent what is happening in the complete structure, we need to keep the balance just to don't over-constrain the simulation more than necessary. So for that reason, we are just applying the roller slider in this internal phase. Okay, let's run this study. And here we have the results. Let's review them. Okay, the first thing that we can appreciate is that now we don't have that twisting effect, or at least we minimize it a lot with this restriction. As we are just restricting this translation, we could appreciate a little twisting, but not as before. I will animate it. We can see a clean movement in the vertical direction. That is what we were looking for. Good. I will exit from here. As we said before, we still can appreciate in the stress plot map a non 100% equilibrated stress along the fork due to the effect of that rotation, but it's minimum. Okay, let's have a look at the displacements. As we were seeing, the behavior of this component is what we were expecting. The movement is in the vertical direction, but the only problem is the value of the displacement. If you remember, before, when we were checking the complete structure, we saw a maximum displacement of 9 mm, and now here we are obtaining a value of 14 mm. What is happening now? Let's review what we have now in this model. In previous videos, we were adjusting each of the boundary conditions. In the top, we have a boundary condition type hinge to represent the relative rotation movement between the fork and the top cross beam. In the bottom, we now are using the wall contact to represent that the structure is just touching the fork and just restricting the movement in the direction towards the structure, but not in the opposite direction. And now we are using the same remote mass as in the entire model, using the roller slider to represent the equivalent behavior done in the entire model. So, to me, this model is quite correct, right? Okay, I need to confess something. If during this series of videos we are talking about boundary conditions and how important they are, when we work with assemblies, the other crucial point are the contact interactions between the components. Depending how we define the contact between each component, the effect will be completely different from the reality. If, for example, here we are using a hinge because we want to represent the relative displacement between the fork and the structure, so when we work with a complete model, we need to represent that effect too. The same with the bottom contact when just touching the structure. Contact interactions are very important topic in simulation. Basically, because in real world, you rarely prepare a simulation of just one component. When we simulate more complete models, we need to think and define how each component interacts with each other. For that reason, I have a complete advanced training related to contact interactions in my simulation methodology training. and we will enter into more detail in coming videos, of course. For the moment, what we are going to do is to review the contacts that the software defined by default in this forks structure model. Let's go back to the structure. Okay, before we touch nothing, how many components do we have here? In the simulation menu, if I drop down the components, we have a few, right? We have this group of components for the fork number 1, this group for the fork number 2, and this group of components for the complete structure. Therefore, the way we define how they interact will give us different results. Some of them will be just in contact, as it's happening here between the fork and this cross member, but some of them will be welded. For example, here between this cross member and the lateral plate, or for example in the top, here and here. This is going to be welded. As you can imagine, the way of defining a contact is not the same way of defining a welded connection. If I go to connections and drop down the menu, here we see the global interaction that the software defines by default. This global interaction is type bonded. I can edit it, right click, and I go to edit it. We can see 3 options: type bonded, contact, or free. We can always change that. But why the software by default is assigning the interaction type bonded? The interaction type bonded is restricting the 3 translations and the 3 rotations in one connection, more similar to a welded connection. The software is doing this basically to assure that your simulation is going to run without problems. This software is very friendly with us, and he wants to give us colorful plots always. But are they correct? Maybe some of them, yes. But as we saw, some of them are not going to be bonded and they will be just in contact. This one or the contact between the fork and the top crossbeam. As I always say, we are here to represent the physical problem in our simulation and not just trusting the first results that we obtain. I will exit from here. Now I go to interactions, right click and select interaction viewer. I press on calculate and here we have them. All of them type bonded. For example, this one between the bottom crossbeam and the lateral plates can be correct since these components are welded. But this one, the interaction between the fork and the structure, should be in contact as we saw before, right? Then, if here we have bonded contacts, the simulation of the fork component is correct since we use the correct boundary conditions. But to compare the results with this simulation, we should define properly the contact interactions between each component. We have here a maximum displacement of 9 millimeters, and in the fork we are obtaining more than 40 millimeters. And this is normal since here we are restricting the movement much more with the bonded contact. If I move to the fork model, I will copy the previous simulation we prepared. I will give it the name of fixed. Again, I will accept, and here basically I'm going to remove the correct boundary conditions that we know that now we validate them, and I will define again this fixed restriction to be comparable with the complete structure. So I will accept, and now I will run. So if we check the displacement, we obtain around 9 millimeters, quite similar to the value we obtained in the complete model. But we know that this is not correct, and what we need to do is to define properly the contact interactions in our entire model. Okay, what we are concluding from all of this? Basically that, depending on what we define in the simulation model, we will obtain different results. And this is great. This is a great news because it's making us the responsible ones of every simulation we run. Not the software, not the artificial intelligence, but just us. I hope that this resonates with you and inspires you to continue increasing your level in simulation. We will continue investigating interesting topics in next videos. And if you want to make the difference and learn how to actually apply all of this in real engineering projects using my validation method, you can find all the details in the description below. Subscribe if you haven't yet. See you in next simulation.